session of the previous year GATE solving solutions. So in the last session we stopped at this point. We were discussing 2022 GATE physics questions. We finished the GA questions and we moved up to the physics part, and we were looking at this particular question. So in this fifth session, I will begin with the quantum mechanics problem. So the problem is given a particle in a box problem. Consider a particle in three different boxes. So you are provided with three different boxes, three particle in boxes, so that they having zero potentials here and infinities after the work. So and also it is given that there is a small perturbation. So it is given that B0 is less than h square pi square 2ml square. So you might be this particular factor you might be recognizing. So in particle in a box problem you have this is like n square pi square h square by 2ml square. So what they have given is that n is a number, n square it will be again an integer value. So by this definition they are saying that this is a small compared to the actual potential. So we can treat it as a perturbation. So this will be a perturbation treatment. Corresponding ground state energies of particles are E1, E2, E3. So box 1 have energy E1, this is E2 and this is E3. The ground state energies in the respective boxes. So what they are asking for is what is the relation between which one is greater, which one is lower. So I have discussed in detail this problem. Going to the solutions. So actually not in detail. This I am doing it only like only the derivations I will show, and I will tell you the tricks how that can be used to like identify without doing integration problems. So perturbation anyway. I will just briefly introduce the perturbation concept. So you have actually unperturbed Hamiltonian, and you perturb it with some small potential, some lambda. So if H0 has eigenvectors psi n with eigenvalues psi n, En, then after the perturbation, if this is the total Hamiltonian H, this will have eigenvalues like En plus up to first order in lambda, delta E1 maybe, and lambda square. This will be a second order correction, etc. so on. And the wave functions will be also having similar correction. So what here we are only looking at the first order correction to energy only. So this is the formula for first order correction. You just take the expectation value of the perturbation in the corresponding state. So like psi n, if the nth state, this will be the correction to the nth state. This is the expectation value of the applied potential in the particular unperturbed state. So these are all unperturbed states, psi 0, En 0, and you just take the expectation value of the applied potential perturbation in the particular state. So doing that here, so first of all there is not much since a given potential, if you look at it, it has a symbol form, like it's a constant for some region and it's 0 otherwise. So in the first case is from 0 to L by 3 it is having a value V0. In the second case, from L by 3 to L by 3, it is having non-zero value, that same V0 value. And the last case, from 0 to L by 6 and L and L minus L by 6 to L, that in that region they are having the non-zero values. Okay, so if you do the first order correction, if you find out the first order correction to energy in this setup, basically you do this in expectation value of the perturbation in the particular state, you will end up with this. So you have integral of V0 will come out because there is no position dependence for the applied potential, it's just a constant. Only the limit you have to be careful. Like in the first case, it's only from 0 to L by 3. So you integrate from 0 to L by 3. Since your V is coming out, your V0 is coming out. So you have psi. That's what this sine square pi x by L. Since it is asked that for the ground state, right? So yeah, so the problem, if you get it is asking for the perturbation in the ground state energy, how the energy ground state energies will change. So you are taking n equals 1. So that's why you are putting there is 1 here, pi x sine square pi x by L. So basically the idea is to only get the integral, this value of integral. So you can do this by like sine square is basically cos. You can express sine square x in terms of cos 2x. So 1 minus cos 2 pi x by L. Either you can do this integration and find out the values and compare these three cases, and you will get. So you can compare them, which one is higher and which one is lower. That you can do. Either that one is fine, or now I will just show you the trick to like identify which one. Without doing this integration, how can you identify which one is higher? Okay, so in the first case, you will get this. If you do this integration, you will get some V0 by 3 constant desires, and there is an integration with this quantity. And then similarly in the second case, you similarly take the expectation value. You similarly end up with the same kind of things, but only in the limit. Now it is from 0 to L by 3. In the second case, it will be, if you look at the diagram, it is from like L by 3 to 2L by 3. Okay, so in this case, it will be like in this integration limit will be from L by 3 to 2L by 3. Same function you are integrating, like integral L by 3 to 2L by 3 sine square it's cos square. Cos square 2 pi x by x. And in the third case you actually have slightly, like there are two intervals in which the perturbation is non-zero. 0 to L by 6 here, L by 6, and L minus L by 6 is what? 6 minus 5 by 6. So from 5 by 6 L to L. So these are the two limits in which you have to integrate. Again you will get some same V0, but since you have L by 6 in 2 times, so you again get the V0 by 3 times and that integration value. Okay, now I will tell you how to identify this integration. You have to compare them without doing that. So basically you are integrating this function in this sine square, you are integrating. So if you plot sine square, this is how it looks like, right? So, in the first case you simply have like what's the first case? Yeah. So if you plot sine square function, this is the only region where you are integrating. So you have to pick up, basically integration is basically the area under the curve. So you have this much contribution towards the integral. This is case 1. Case 2, whereas you are integrating from L by 3 to 2L by 3. Here if you, this is like not may not be a very technical argument, but it's a hand waving argument. But this kind of like in tests where you need to solve problems within lesser time, this is fine. And you have to have some skills to like get the problems done within lesser time. That should be your motto. And the third case, of course, this is the case too. You have some small, yes. Again, you have sine square integration, but you are now taking only small here and here. There are two limits here. So if you look like in the second case, the contribution is higher. The area under this curve is, this one is higher actually here. Whereas the third case is the lowest and highest, and this will be the intermediate. So that's why we can easily identify that B is greater than A and which is greater than C, and C is the least one and B is the highest one. So that means the energy correction to the first order energy correction to the ground state is higher in case 2 than in case 1 and then second the last case. That means the first order corrected energy is like in the ground state first order corrected energy is E2 greater than E1 greater than E1. This should be your answer. Okay, so actually in principle you have to do the question is ground state analysis of particle. It's not up to first order correct the actual correction, but since all the other corrections are like second order and higher order terms are similarly also, they will be also having same kind of patterns, but the most contributing term will be the first order. Then you can confidently go for the first order correct value. So that's why you get the correct answer, the option A, which is second one is the highest energy and least one is the third case. Second, the first one will be the intermediate. Okay, so this basically like the idea is to you have to remember only the what is the formula for the first order correction and how to do this without doing actual integration. Okay, so this kind of tricks not always work, but when there are this like cute looking functions where you can make some guess, you can do this kind of guess. Okay, so next problem. A power supply has internal resistance Rs and open load voltage Vs, which is 5 volt. When a load resistance RL is connected to the power supply, a voltage drop of VL equals 4 volt is measured across the load. So what is the value of RL by Rs? So I have drawn the diagram here. So you have a power supply which is having an internal resistance. I denote it with Rs, denoted in this problem also, and also you are connecting a load resistance RL to the circuit. So open loop voltage means the voltage when there is no load is connected here. So that should be the like it's the EMF of the cell. So if you connect such a, now if you when you close the circuit, basically you have the internal resistance of the cell and the load resistance in series to the total EMF, right? So that will give you a current of I equals V0 divided by V0 is a EMF divided by RL plus Rs. That will be the total current in the circuit. Now they have given that there is a voltage drop of 4 volt across the load resistance. So that means current times by Ohm's law we have like V equals IR. So whatever current flows through some resistance R, it will be having a potential difference or voltage drop across that by a number I times R. Using that here, we basically have the potential difference across the load resistance RL given by V equals IRL. Is only the RL, not RL plus RS, but only RL. V0 RL divided by RL plus RS, that you will get, it is given that it is 4 volt, right? So it is 4. Now you just have to rearrange. V0 is actually given, it is 5. So basically Rs plus RL divided by RL will be given by, you take this side and you will get 5 by 4, and again you have some simplification. RS by RL is 5 by 4 minus 1, which is 1 by 4. The question is RL by RS, so you have to take the reciprocal again, so that means RL by RS is 4. So that's answer to this question. Answer is 4. So these are numerical type questions. You have to answer by a number. Okay, so the next question is Lagrange's from classical mechanics. If x dot y dot plus alpha xy is a constant of motion of a 2D isotropic harmonic oscillator with a Lagrange, so you are provided with a Lagrangian, then what is the value of alpha? So find out what is the value of alpha such that x dot y dot plus alpha xy is a constant of motion. So constant of motion means it's a conservant. So constant of motion means it's a conservant. So over time, the value of the quantity does not change over time, like energy conservation and momentum conservation. This quantity is conserved over the time evolution. Okay, so how to do this? This is one of the way to do this problem. Actually, there are several ways to do this. I'm taking a different approach. Maybe I think with the Lagrangian itself you can do the problem. So what I do is I basically convert the Lagrangian into the Hamiltonian. Usually L is defined as T minus V and H is defined as T plus V, the total energy. So here if you look at this, you have the velocity terms here, x dot and y dot, and you have the coordinates. Since it's a 2D isotropic harmonic oscillator, you have the half kx square kind of spring constant force, spring force here. So you can simply make this plus to get the Hamiltonian T plus. So usually be aware that this is not that easy. Like given a Lagrangian, you have to find out the Hamiltonian. It's not that this kind of simple task, but usually you have to find out what are the coordinates. For example, dou L by dou x will give you px, like that. So you have to find out what are the canonical momentum and associated to every coordinate. There will be a conjugate momentum. You have to find out that, and that way you have to find out what is the Hamiltonian. So in this case it's actually easier, so that's why I took this way. So you will get the Hamiltonian as it's writing here. If you replace x dot with px, like in the Hamiltonian language you actually have coordinate and the momentum also. So the first term is basically px square by plus py square by 2, like just the total momentum of the particle, and the second term is the total potential. So this is k by 2 x square plus y square. So where x, px are the canonical conjugate variables, such that the Poisson bracket of x ps will be 1 and Poisson bracket of y py will be 1. Okay, so this will be the Hamiltonian of the system. Now given the Hamiltonian, knowing that Hamiltonian also, okay, this is also something you have to. So they have provided with a quantity like x dot y dot plus alpha xy, right? This also you convert in terms of px py. So px is basically x dot divided by mx dot, m times x dot, and py is basically m times y dot. So replacing x dot in terms of px, you will get this is basically px py divided by m square plus alpha x. this is the operator or the quantity you are going to look at. So given that this quantity O is a constant of motion, so constant of motions happen when the Poisson bracket of Hamiltonian with that that operator, or sorry, operator comes in the quantum mechanics language with that quantity O is 0. So this happens because you have this fact: the total time derivative of any quantity do by dt is given by the Poisson bracket of H with O and the partial time derivative of that quantity with respect to time. So in this case, at least, there is no explicit time dependence, right? There is no time explicitly in that functions. So we can safely this will be going right away to 0, and total time derivative is given by the Poisson bracket of H with O. So this is a constant of motion, means this is 0. This total time derivative is 0, it does not change over time. So you have H, the Poisson bracket of H with O is 0. Now just apply the expand the Poisson bracket H with O. So the definition of Poisson bracket is this: H O is sum over I. How many conjugate how many coordinates you have to sum over all those coordinates. Dou H by dou Qi are the coordinates, and dou O by dou Pi minus dou H by dou Pi and dou O by dou Qi. Okay, so this is the I'm just reminding you the Poisson bracket. So where Q, P, these are the conjugate variables. Okay, so applying this in this particular case, you have two conjugate variables x and xpx and ypy. So you just take the derivative: dou h by dou x is kx, dou o by dou px is py by mc. Just try to do these calculations, then you will get the same results. So dou h by dou px is px by m, and dou o by dou x is alpha x. Similarly, you doing the same things for y also, you will get this, and from here you can actually will get this kind of relation. Xpy is here there is an xpy, and also here there is an xpy. You can take that out and you will get a k by m square minus alpha by m. And also similarly, you will get a ypx here and a ypx here. There also you will get the same factor here: k by m square, alpha by m, and k by m. Same quantity comes up, and this will be equal to 0. Given that it is 0 because it's a constant of motion. So this happens. The question is, what is the value of alpha? So you make it 0, and you can make this 0 when this individual quantity, this k by m square minus alpha by m, is 0. That happens when alpha is k by m. So it's plus k by m. So if you look at the options, you have plus k by m. So this is the right answer. Okay, so what I did is there are other ways to do this also. I am just taking the method which is easier for me, at least. So I convert this Lagrangian into Hamiltonian and find out the coordinates, the conjugate momenta px py. Then I apply the commutator HO is, and that will give you what is the value of alpha. Okay, so yes. So this one is not it's just a qualitative kind of question. The question is, at T equals 0 Kelvin, at absolute 0, which of the following diagram represent the occupation probability of energy of states of electrons in a BCS type superconductor? So BCS is the Cooper pairs theory of the superconductivity, and you just have to say in which of the following probability distribution actually gives you the occupation. So the first look, even at the first look, you can actually discard these two, this one and this one, because of the unphysical nature of that. Because at any temperature, uh, here what it's shown is that the lowest energy states are not at all occupied, but the highest higher energy states are occupied. And here also same kind of, these are like, this is very unphysical, this does not happen in reality. In real world, like the lowest energy states will be the always occupied states. And this happens like when, like in the case of laser, when there is population inversion or something. When you, population inversion means you basically populate the excited states by pumping some energy into the system. But this does not like in a, when you have equilibrium states or something, this does not happen. So these two you can simply discard. Now what about this? This is basically, if you might be remembering the fermion nature of like in, when the if you look at the fermion probability the distribution function, E minus EF by KBT minus 1 minus, oh sorry, plus 1. So when t equal to 0, this is basically like you have infinity, either minus infinity or plus infinity. So depending on that, when E is E minus E is less than the Fermi energy, all the states will be occupied. So maybe I might be wrong here. E minus EF means for E, E minus EF is less than 0 if E is less than 0, right? Yes. So that means if you take this exponential at t equal to 0, when you have you have e raised to minus infinity, e raised to minus infinity is 0, then you will get a 1, this kind of probability distribution. Whereas in the other case, if you have E minus EF greater than 0, in the case when E is greater than EF, when your energy is greater than the Fermi energy, then you have e raised to infinity here, which is infinity. So 1 by infinity is 0, then this will go to 0. So this is basically the fermionic distribution for the only for the fermions at t equal to 0. So in our case, the given case, the BCS superconductors, these are not fermions actually. These are kind of composite particles. Two electrons combine to form a bound state, Cooper pair. So this does not behave as fermions. So there is a difference between fermions and the Cooper pairs. So that's why you can discard this option also. This is the right answer. I'm not sure whether at least I don't have like this distribution. We don't learn the BCS theory, etc. Even the MSc syllabus. So just be aware of the fact that this is the distribution function for the BCS superconductor at t equal absolute 0. Okay, so next, this one is again quantum mechanics. Question from the quantum mechanics. So just for a 1D harmonic oscillator, the creation operator and Dagger and state, so they have provided you how the creation and annihilation, annihilation is not given here, but it is evident. A Dagger acting on psi n will give you root of n plus 1 times psi n plus 1. So the matrix representation of the position operator is given. Okay, so that is what you have to find the matrix. What is the matrix representation of the position operator for the first 3 rows and columns? So basically here you have n goes from 0 to infinity, right? So first 3 rows and columns means you only have to take 0, n equal to 0, n equal to 1, and n equal to 2. Okay, so in that case, what will be how the position operator will look like? That is the question. Okay, so this is how this is just a matrix, you have to find out the matrix elements. That's all. Straightforward question from quantum mechanics. You can easily do this kind of question. If you practice, you should have some practice, of course. So operator is given to you directly, position operator, apposite dagger, and the effects are also. So this should be something like you can remember. It is better to remember these relations all, even if they are not providing. It's very easy relations actually. So when a dagger acts on psi n, basically takes to the higher energy states, takes upward, and when a acts on n, it takes it down. And the factors are also like when how I usually remember is the factor is always the highest number here. So when n goes to n plus 1, it will have a root n plus 1. When n goes to n minus 1, again it will have a root n, the highest number. So that's how we remember that. And taking the first three rows and columns, psi 0, psi 1 and psi 2, you basically have a 3 by 3 matrix. 1, 2, 3, 4, 5, 6 and 7, 8, 9. So these matrix elements are these. So the first element will be psi 0 x psi 0, which is 0 because if psi 0 x is acting on psi 0, it will either take like A will act on psi 0 will give you 0. It will just annihilate that state. But a dagger acting on psi 0 will take you to psi 1 with a factor of 1. So now you are taking the inner product with psi 0 again, whereas the state does not contain psi 0 after the operation. So you will get 0 here. Similarly, in any diagonal elements like it acting on nth state, it will either take the x operator will either take you to n plus 1 or to n minus 1. And whenever you take like n x n kind of matrix element, you will always get 0. That's why you are getting in this case this matrix element is 0, where you take psi 1 x psi 1 and also psi 2 x psi 2. So these three are already not you don't even have to do the calculation to get this. You can directly see them, they will be 0. So from that you can actually like if you look at the options, you can discard this option, because there will not be any diagonal elements in the matrix. So your options are now only two more options are left. Okay, so now look at the other elements. So what about psi 0 x psi 0 x psi 1? Okay, so psi 0, when x acts on psi 1, basically it takes to, it can either goes to psi 0 or goes to psi 1, psi 2. So this will happen with a factor root of 2. This will happen with a factor root of 1. So root of h cut by 2 m omega is already there with x operator, and you have a root 1 here. When you take the project it on to psi 0 again, you get this factor. Now when you get project on to psi 2, you get root 2. That happens. Okay, I will come to that. So that's how you get this root 1 here. Now this matrix element psi 0 x psi 2. Okay, so here also these are also easier to see. When x acts on psi 2, basically it goes to either psi 1 or psi 3, right? Whereas now there is a gap of 2 between psi 0 and psi 2. So this is again 0 because these are all orthogonal states. Like psi n and psi m, these are delta m n. Only when m equals n, this is 1. All other cases it will be 0. So that will give you a 0 here, and that readily will give you 0 here, because x is a Hermitian operator. The matrix element should be like the matrix should be Hermitian. A should be a dagger. So this entry and this entry should be like complex conjugate. Since this is 0, this one is also 0. So if you get this term, this particular element here, you can directly get what is psi1 x psi0. This is the complex conjugation here, and that will give you the same because it's a real value. So now you are only we have to only find out the last, this one. So here when psi2 x acts on psi2, it will take psi2 will either psi2 will go to either psi3 or psi1. Now you are projecting with psi1, right? So this will happen with the factor root 2, and this will happen with the factor root 3. So that's how you get a root 3 here with the root h cut by 2 omega factor. So with the Hermitian property of hermicity of the position operator, you will get this number also. Now you have evaluated. So the idea is that you have to only evaluate only like lower left or up, either the upper elements or the lower elements. The other elements you can directly get because of the Hermitian property. So just writing out the matrix elements, you will get the matrix. This is how the matrix looks like. You pull out an h cut by m omega factor, 2 m omega factor, root of factor, and you get this. So this is not the possible one, so you have obtained this. It's just an exercise with the matrix elements. Okay, so the next in the next case you okay, so a particle of mass m is moving inside a hollow spherical shell of radius a, so that the potential is given. So inside the sphere there is no potential, it's 0. Outside the sphere it is infinity. It's like a infinite, like a square well potential, but it is not a well, but it's like a shell. You have to only pick out which are the correct options. Okay, so let's look at the options. The first option is that the E0 equals h cut square pi square 2m square. If you remember, this actually like the infinite potential well actually have the eigenvalues h square pi square h cut square by 2ml square. So when L equals A, there it was the width of the well, right? This is a L, but here it is the radius of the shell. So actually this is the same, like in the ground state energy of the spherical shell and the ground state energy of the particle in a box, they are similar, given that the length of the well is equal to the radius of the shell. So this is something you should be remembering. You can actually derive this energy eigenvalues. So this is true, this one is true. Now the second option, this is basically you have this derivatives all here. This is the Schrodinger equation written in the position basis actually. So basically what you do is write down the Schrodinger equation in spherical polar coordinates. So h psi equal e psi. H is what? P square by 2m. There is no potential. V of r is basically 0 inside the radius, right? So basically this will go up. So then you will get apply the P's the momentum operator, you will get minus h cut square by 2m del square. Del now you have to express in the spherical polar coordinates. So this is something actually it's not very easy to remember, but at least for the purpose of the exams you should be remembering these expressions. So this is how the del square, the Laplacian looks like in the spherical polar coordinates, this particular form. You apply it on the wave function, and since you can actually perform the separation of variables in this case, like in the case of hydrogen atom, the r theta phi, you simply pull them apart. R of r is capital R is function that depends only on the radial function, and phi of theta and phi will be like the angular part, or it's azimuth. I mean, it's a Legendre polynomials will come in that PLM, YLM, it's two quantum numbers L and M. Same will come happen whenever there is a like spherical symmetry, like there is no change in the potential by when you rotate the system or something. It's, like that. When it has a rotation symmetry, it always has this spherical harmonics. So these are the spherical harmonics for like hydrogen atom, etc. These all these kind of state systems, you can find out the spherical harmonics. Okay, so that was just an information. So if you now make the variable separation, you put psi of r as r of r times y theta f, then there is only like this r dependence derivatives only happens on capital R. Then you will get this minus h squared by 2m 1 by r square dou by dou r square dou capital R by dou r is E0 r. Right side is just the eigenvalue. So this is written for the ground state energy. So that will give you option B is the right answer, whereas option C is just some like looks like option B, but it's wrong. So option B is the right answer. Now how to get what they are saying is they are giving the form of the radial function r of r. So you have to check whether it is right. So how to check this one? Option D, you can just plug in that in option B. Since you already obtained option B is right, you just plug in the value of r of r in option B. Then if you are getting back your E0, that is option A, then you are done. Okay, so I'm just putting r of r in that equation. Take the derivatives here. You try this, work out this problem. So you will get a chain rule derivation here. That's how you are getting a sine and cos here. Whereas in the second time when you differentiate, one of the term actually cancel out with the other term. So this term will cancel out, and you will be ending up with only one term. That will be this minus pi square a square pi square by a square sine pi r by a divided by r. This actually you can okay, so there is this term also minus h square by 2m also. Sorry, this minus h square by 2m also. If you put that also, you will get basically pi square h square by 2m a square times sine pi r by a divided by r. Now what is your r of r? Is just 1 by r sine pi r by a, and that's what you are getting back here. So this is basically your r of r, and if you look at this factor, it is E0. So you got if you put your r of this particular form of r of r in your equation B, you will get back E0 as well as your D also. So that is also a valid option. So option A, B, D are right. These are right answers. Okay. So these two questions are not much to do. It's conceptual questions. Electronic specific heat of a solid at a temperature T is C is gamma T is proportional to temperature. So you have a solid and it contains a contribution due to the electrons and the contribution due to the lattice, the phonons, etc. You might have seen this like in metals, your specific heat have two parts like gamma T and some other beta TQ. So this will be due to phonons and this will be due to electrons. Okay, so this part they are talking about. Gamma is a constant related to the thermal effective mass of the electrons. Then, which of the following statements are correct? So, following these are the right answers. So, gamma is proportional to the effective mass. So, when effective mass of the electrons increases, the coefficient gamma increases. M effective is greater than free electron mass for all solids, which is not true. This is not true. Temperature dependence of C depends on dimensionality, which is not true, because it depends only on, it's a property of electrons only. So this is independent of in what kind of solid it actually resides. It's a kind of universal kind of behavior for electrons in free electrons kind of case. So the last one, the linear temperature dependence of C is observed in the T less than T by, which is true. Like in the closer to D by temperature limit, you basically this will be the like prominent. So this is T. When in the smaller temperature, this becomes prominent. So this is also the option D is also true. So A and D are the right answers. And the next problem, a Hall effect experiment on an intrinsic semiconductor. Which of the following statements are correct? So Hall voltage is always zero, which is not zero. Hall voltage can be non-zero. So when you apply a magnetic field, so basically the Hall experiment is that you have a conductor. Here it is intrinsic semiconductor. Anyway, you will have some conducting channel. You apply some magnetic field perpendicular to that. So that will, due to the Lorentz force, there will be a like applied. There will be a developed potential across this channel, which is called the Hall voltage. So this is called the Hall effect. So as far as there is a magnetic, this voltage depends on the strength of current and the strength of the magnetic field as well. So as you change, you also the it depends on the carrier density and exit. How many carriers? How many? It depends on like basically the nature of the metal you are using. So Hall voltage is not always zero. So this one is not correct. Hall voltage is negative if the effective mass of holes is larger than those of the electrons, which is not true. So this is, I am not very sure about this. Effective mass of holes is greater than electrons means, so their mobility of the holes will be less than, because the more massive the particles, they will be lesser mobile. So this one is higher in mass means it cannot move much. So holes cannot move much. So that should mean that this in the other way around, like the Hall voltage should be positive in that case. That can be a reason why this is wrong. And Hall coefficient can be used to estimate the carrier concentration. This happens in the case of metals. So semiconductors, I am not very sure about that. So this is also a wrong answer by the key. And of course, the Hall voltage depends on the mobility of carriers, which is true. So if they are too mobile, then the voltage will be higher. If they are not that much mobile, then the voltage will be lesser. Okay. So how much time we have? We have around 10 minutes. We have two, three questions. Try to cover that. A parallel plate capacitor with spacing D and area of cross section A is connected to a source of voltage V. If the plates are pulled apart quasi-statically, so you have a parallel plate capacitor. So if this is D now, what they do is they pull apart this plates. Now after that you will get a distance of 2D after the process. So they move it apart quasi-statically, that means very slowly. Which of the following statements are correct? So actually I am not a little confused with this problem because I part of it I worked it out. So the capacitance of such a parallel plate capacitor is given by C is equal to epsilon A by D, and the energy stored in the capacitor is half CV square. Right. So initial and final energies will be like half epsilon A V square by D, and half epsilon. There's an additional 1/2 factor here because of the doubling of the separation. Now the change in energy is E2 minus E1 is negative. It's given here. So the energy of the capacitor reduces by, so this is something I am getting, this is true, and they have getting A and C are also marked as the right answers. I have calculated the force actually because I am not getting the exact factor that they are getting. So we know the electric field inside the parallel plate capacitor will be sigma by epsilon, where sigma is the charge density, like Q by A. If Q is a total charge and A is the area, then sigma is basically Q by A. So actually that you can write in terms of V. So Q equal to CV by the capacitance relation. So C is something for the epsilon A by D, that's already we know for the case of parallel plate capacitor. So A and A will cancel out, and this will be your surface charge density epsilon V by D. So using this sigma here, you will get now what is the total force? Force is basically QE, electric field. So there is an electric field here, and if you have this much charge on this plate, then there will be like a force acting on that due to this electric field and presence of the charge. That will be given by QE. So sigma A times E, you will get this. When you work it out, you will get epsilon A V square by D square. V square by D square. Yes. Now what they are asking, at a distance, at a spacing of 2D, what is force? So when you put D equals 2D, basically you will get only 1/4. But actually they are getting a 1/8. So this factor I am not very sure about. There can be mistakes in the key as well. So I am getting the option 1/4. So if D equals 2D, I will get a 1/4. Now work done in moving the plate is this. Now what we saw here is there is a minus sign, right? So energy is actually decreasing, so we don't have to do any work to do this. So that's why this option 2 is not true. Now the energy transfers to the volt. Again, this is also I am little confused because so the change in energy will be the energy transferred to the source. So this will be the same as far as I understand the problem. So this should be a 1/4 here. So these two options I am not very confident about. So but these are the marked options A, C and D. Okay, so this one is something we can work out. Okay, so a system with time independent Hamiltonian H of QP has two constants of motion, F of QP and G of QP. Then which of the following Poisson brackets are always zero? So again we already encountered a question regarding the constant of motion. So this is again in the same line. So constant of motion happens when the Poisson bracket of H with that quantity is zero. So here F and G are themselves constant of motion. That means F and Hg both are zero. You have to use this in this. So the first option F plus G there is anyway because F and G are individually constant. F plus G will be another constant of motion. So this one is true. Now the second one, this is you have to apply some other identity. It's called Euler's identity. So H F G plus basically you have all three possible permutations, cyclic permutations, G, HF and FGH. All these commutations add up to give you 0, which is called the Euler's identity. Now, as per the claim, HF and GH, the HF and HG, these are two things 0. So that means that HFG is also 0. So you combine your Euler's identity with the given fact, then you would get HFG is also 0. So this option is also true. What about H plus FG, the option C? There actually you have HG is here, which is 0, but FG is not necessarily 0, because these are two different different quantities whose computation relation, the Poisson bracket, you don't know what it is. So this need not to be necessarily 0 unless it is given. The last one, H with H plus FG. This is a trivial Poisson bracket, it's 0. H with FG, again F and G are individually constants of motion, then Fg is again a constant of motion, because F and G are individually themselves a constant of motion. So this is also 0. So this should be minus, should not be plus, but just H with Fg. This should be 0. So that means option D is also fine. So only option C is the is not 0. It's not 0. Everything else is 0. Okay, so how much time do we have? Enough time? Or we only have 3 minutes? Yes. Let's see. Maybe this one also we can. Particle of mass m in xy plane is confined in an infinite 2D well with vertices 0, 0, 0, L, L, L and L0. Basically it's a square with 0, L with lengths 0 and L. So eigenfunctions of this particle are basically combination of two particle in boxes, one along x, one along y. So if perturbation of the form V equals Cxy is applied, where C is just a constant, which of the following statements are correct for the first excited state? Okay, I have worked it out. So basically this is the potential looks like, and the eigenfunctions are given to you. Psi nx ny is 2 by L, sin nx pi x by L, and sin ny pi y by L. And that means the energy eigenfunctions are energy eigenvalues are basically you just combine two energy eigenvalues of particle boxes with quantum numbers nx and ny respectively. So that will give you nx square plus ny square pi square s square by 2ml square, where nx and ny can take values from starting from 1 and going up to infinity. So the ground state will be when this quantity is the least one, nx equals ny equals 1. They are asking about the first excited state here. So that happens when nx equals 1 or and ny equal to 2, or nx equals 2 and ny equals 1. This is also possible. So there will be degenerates. But the energy eigenvalue here is just you just add nx square plus ny, so you will get 4 plus 1, which is 5. So 5 by 2 pi square h square by ml square is the first excited state. So this is wrong and this is true. So this is unperturbed energy without applying the perturbation. What about the C first order energy shift due to applied perturbation is 0. So let's see. Option C, we have the applied potential V of xy cxy. Now the first order correction to energy is, as I told before, just the expectation value of that given perturbation in that state, which here is not zero. By you can have intuitions on these kind of scenarios without doing this integration. Either you have to do this full integration. This is basically two-dimensional integral. You have two variables x and y. Either you have to do this completely, or you can simply guess this from the how the wave function looks like. So this is your wave function. I am just showing only one dimension. The other dimension will also look like the same. Say this is x. So your first excited state wave function will look like this. So you have one node here, and your applied perturbation is c times x, right? It's a linear function in x, so it will look like this. Now if you take the integration of this will give you like there is nothing you cannot tell you about like how this will there is no parity hidden here to say that the integration will give you zero. So this is not zero. The contributions are actually happening from all these points, and you can get that this is non-zero. This is a non-zero integral, and that means that the given option is like it's given that it's always zero, which is not true. And the last option is that the shift in energy due to the applied perturbation is determined by an equation of the form. It's a determinant of 2 by 2 determinant where A and B are real constants. So as I told just before, the first excited state is twofold degenerate. So you have either nx1 ny equal 2 state, or ny equals 1 nx equal 2 state. These are two degenerate states of the first excited state. So you have to apply the first order, the degenerate perturbation in that state to lift the degeneracy, and that will be effectively boiling down to a problem of solving. You basically represent this potential, applied potential V of xy equals cxy in the n. So you have two states, nx equals 1, ny equals 2, and nx equals 2, ny equals 1. This is a subspace, degenerate subspace. So in this subspace you basically represent this your V of xy by finding out the matrix elements. There will be 4 matrix elements, and you diagonalize that matrix to get that will be in this form, and you diagonalize that. That's basically this eigenvalue problem. So finding out that eigenvalues will give you the shift, how the degenerate states will shift into non-degenerate states. This shift will be given by these eigenvalues. Okay, so that's how the options D is true, B is true, whereas A and C are not. Okay, so I think we are out of time. Yes, so we can stop here for today. We will come back with the last session for this in the next session. We will finish up 2022. Thank you.